I built a 3-in-1 console that can play the Switch 2, Xbox, and PS5 all at the same time. With the press of a button, you can instantly switch between all 3 consoles. These 3 are the titans of the current gaming world: the PS5, the Xbox, and the Switch 2. Throughout history, these 3 have always been in fierce competition, the console wars. This means that games from one company often can't be played on another's platform. So, if you want to play a wide variety of games, you have no choice but to buy all 3 and constantly switch between them. For them, it's a decision that certainly makes business sense, but for me, it's just a huge hassle. So I decided to combine all 3 consoles into one, to create the ultimate gaming machine.
To bring them together in sync!
As a symbol of friendship between the 3 parties, to finally end the console war. But if I just tie all 3 consoles together, I'm left with a 19-liter, 10-kilogram hunk of metal. It's not elegant, so I have to help them shed some weight. Taking apart the 3 consoles, you'll find the main components are always the same: the motherboard, the cooling system, and the power supply. The motherboard, despite holding all the electronics, is actually quite small. It's the power supply and cooling system that really take up all the space. So I thought, what if the PS5, Xbox, and Switch 2 could all share one power supply and cooling system, and just switch between them? That way, I could get the power of all 3 in the space of just one. The plan is simple. You think it's as simple as connecting a few wires and 3D printing a case? Seriously? How can I design a cooling layout that keeps all 3 machines from overheating? Huh? The answer is right here, the Mac Pro trash can. The best looking Mac desktop in my opinion, and its internal design is also really special. The heatsink is right in the center, a very sci-fi looking triangular prism. 3 motherboards are attached to its 3 faces, and a fan at the top pulls the hot air out. Even though Apple bet on the wrong horse with dual GPU technology, which meant this Mac Pro never got a successor, it's the perfect blueprint for our 3-in-1 console. After some simple modeling, I had a prototype design for the heatsink. All I needed to do was CNC an aluminum version. Huh? 5,000 yen? Because it's so large, and maybe because of all the intricate grooves. The CNC process is extremely complex, which makes it very expensive. For the same design, metal 3D printing is also incredibly pricey. Plus, outsourcing production means waiting in line and dealing with long lead times, which isn't great for rapid prototyping and testing. It was at this moment that I made a decision I would later come to deeply regret: casting it myself. Of all the ancient methods for metalworking, there's one technique so brilliant it's still impressive today. It's called lost wax casting. To create intricate bronzeware, directly carving the metal itself isn't very practical. So the ancients would first carve the much softer wax. Then they'd cover the wax model with clay. And by taking advantage of wax's low melting point, they could melt the wax out, which also fired the clay, cleverly leaving them with a hollow ceramic mold. Then they'd pour in the molten metal. This cloud pattern bronze djinn from 1500 years ago was made using the lost wax method. And here I was, naively thinking these were all just chiseled out with a hammer. I bought some carving wax and tried to carve a 5-pointed star. I definitely wouldn't survive Squid Game. Carving on wax is not for me. But in 2025, you don't necessarily have to use wax. Wax is just easy to shape and has a low melting point, so what else could give me a solid meltable object? Of course, 3D printing! In theory, 3D printing is also easy to shape, allows for fast iteration, and the most common 3D printing filament, PLA, also has a very low melting point and is inexpensive. Most importantly, I have all these printers ready to go. To go with the PLA, I picked a high temperature plaster for my mold. PLA melts above 100 degrees C, pyrolyzes at 300 degrees C, and burns away at 700 degrees C. The high temp plaster can be heated to 700 degrees C without breaking. By using their different heat resistance, I can remove the PLA and get a clean mold. This method is called the lost PLA method or the lost plastic method. This is the PLA model I just printed. This is the main body of the heatsink. I also printed this extra part. This is the channel for the aluminum. The aluminum will go in here and fill all the heatsink fins from the bottom up. It's designed to fill from the bottom up to make it easier to push all the air out. Next up is making the mold. I'll mix the high temperature plaster powder with water, stir it quickly, pour it into a stainless steel bucket, and then place the PLA model inside. Then before the plaster sets, I'll quickly put it in the vacuum chamber. I'll pump the air out of the plaster. The whole thing looks like it's boiling, bubbling away. This process is called degassing. After degassing, I'll wait for the plaster to set at room temperature. I didn't realize the plaster accidentally covered the top of the model, so now I have to painstakingly dig the opening back out. Colleague, use this! It's got more power. It feels like I'm excavating an artifact. Once it's cleaned out, it can go into the high temperature electric kiln for the burnout. This process will take 12 hours and go through 4 heating stages: drying, pyrolysis, burnout, and finally, holding the temperature to get ready for the molten aluminum. Just in case there's any ash left inside, I'm using high pressure air to blow out any remaining dust. As you can see, the plaster surface captured a lot of the PLA model's details and it's perfectly intact. I'm surprised the PLA could burn off this cleanly. How interesting. Next step, melting the aluminum. Turn on the gas and light it up. Inside the furnace, a beautiful blue flame vortex appeared. The aluminum pellets I placed in the crucible earlier quickly started to glow red from the bottom and soften. After a little while, it reached its melting point of 660 degrees Celsius and completely melted into a silvery liquid. At this point, I have to take a long ladle, and just like skimming foam off a hot pot, I skim off the oxides and impurities from the surface of the molten aluminum. It looks funny, but this step is actually very important. Finally, I take out the preheated mold. While both the mold and the aluminum are still hot, I quickly and carefully pour in the 700 degrees Celsius molten aluminum. I quickly realized that about halfway through, it was getting a little hard to pour. I think the aluminum cooled and solidified too quickly, so the rest of it couldn't get in. After cooling it in water and breaking off most of the plaster, I got the result of my first casting. Even though it's not a success, I'm still pleasantly surprised by the result. The surface is pretty smooth and the edges are very sharp. It even reproduced the support layer lines from the 3D print on the bottom. Besides the aluminum solidifying too fast, there were 2 other issues. First, the heatsink fins are a bit too dense. The plaster wall was too thin, so it started to crack at the ends. Second, the heatsink fins are parallel to this edge, which makes this section very long. But those aren't major problems. I just need to adjust the orientation, thickness, and density of the fins, and it should work. You know, I realized that when you fail, that's when the advantages of 3D printing really shine. When ancient craftsmen failed, they had to carve a new wax model by hand. I fail, I'll just print another one. I adjusted the temperatures of the plaster mold and molten aluminum. This time, the aluminum filled the mold before solidifying. After dissolving the plaster in water, the aluminum piece emerged perfectly, like a lotus from water. After sawing off the extra sprue, sanding, and polishing, the fins are intact and look great. The 2 sides that contact the PS5 and Xbox motherboards are flat. The third side still has a few craters from trapped gas-forming cavities, but this side is for the Switch too and doesn't need to dissipate heat. So, the aluminum block heatsink casting project is a success. Honestly, I didn't expect it to work. The lost wax method is truly the GOAT. Next, I'm using pure copper, a metal with amazing thermal conductivity, to make mounting plates. Then I'll use screws to attach them to the aluminum heatsink. Their job is to evenly spread the heat from the chips onto the surface of the aluminum. The PS5 originally uses liquid metal as its thermal interface material, but since we have pure copper and this massive aluminum alloy, regular thermal paste will be enough. Next, let's install the motherboards. I'll place a 12cm cooling fan underneath the heatsink to blast air upwards, and then we can power it on and see. It's on! The French ring has been here for half an hour now, and there has been no indication of a heat test. In fact, the entire area is only 60 degrees Celsius, and the heat has indeed been transferred very well from the chip to the aluminum block. Mission accomplished. Regarding the power supply, my initial idea was quite complex. I planned to design a 3-stage switch that would power the device only when needed, working on each switch in turn. However, this approach was cumbersome, requiring the console to be powered off before switching, and the circuitry would be very complex. Then I calculated that while the PS5 has a 225-watt load, its standby power consumption is only around 4 watts, making it very power efficient. The Xbox is similar. Then I don't need to switch anymore. A 250-watt PC power supply will suffice, as long as I don't run 2 games simultaneously. Besides, both the PS5 and Xbox Series S motherboards use 12 VDC, so I can just connect them in parallel to power the Switch. For the Switch, I just need a transformer and a DC to USB-C right biased converter. Speaking of Switcher, I have other plans for him. As the main unit, it needs to be detachable and portable, so I reserved the third face of the triangular prism for it and made a new custom base for it. Actually, the original Switch base wasted quite a bit of space. After removing it, only these 2 items were useful. As for the fan, you all know it's not for cooling the Switch. It doesn't even reach the console. I understand that it's meant to prevent the Switch's mainboard from overheating due to the heat from the Switch's 2 main units, and to provide cooling for the dock. Since we already have a bottom fan blowing upwards, we don't need this. The weight-reduced base looks like a small square box. Opening it reveals an L-shaped Type-C extension cable connecting to useful electronic components, which will all be placed inside the chassis. This small box will be attached to the last surface of the heatsink, and then the Switch will be installed. Ta-da! But how do I take it out? I'd like it to have a bouncy feel like a toaster. It could be easy to achieve. Make a platform at the bottom of the box, install a spring on the back of the platform, and when I insert the Switch 2, the platform would be pushed and locked into the cutout in the front cover. Then I just need to press the spring clip to pop the Switch out, but the spring's force is too weak, not even considering the resistance the USB-C port might provide. Later I tried several other springs, but none of them worked, except for a metal spring. What? Other materials can be elastic too? Then I thought of plastic springs, which are quite common in 3D printing. I found a 3D printing spring generator on MakeWorld, which allows input of various thicknesses, lengths, and widths with customizable values. No modeling is needed. I've generated a whole bunch. This not only allows for quick and iterative trial and error, but also results in one-piece molding, saving the hassle of assembly. The entire lower jaw spring is one-piece molding, as is the upper shell button. No assembly is required. Once printed, the button is movable. Furthermore, to prevent this movable part from sticking to the base, 2 different materials were used. PLA for the outer shell and PETG for the spring, ensuring spring rigidity. Using the dual head printing function of the Giorgio H2D, 2 materials are printed out from 2 separate heads. Usually dual heads are for multicolor acceleration, but they can also print complex dual material models in a pinch. This way, as soon as you take it off the print bed, the spring is already functional. And if we take a cross-section, you can see another little design detail. The PETG spring is embedded directly into the PLA, so it will never come loose. Next, let's 3D print a case and assemble everything. First, let's secure the Xbox motherboard to the heatsink. The bottom triangular box is for the power supply. Inside is a GAN power supply, which powers the entire console. The small holes around are for air intake, because just above it, in the middle, is the fan compartment. Just snap the fan in and secure it. The fan will then pull cool air from the bottom and send it upwards. And on top of this, we'll place the main body of our console. I'll use an L-shaped 3D printed part to secure the heatsink to the case. Then, connect the power for both consoles. Now for the secret ingredient, an Arduino and a circuit board. This will allow us to switch between consoles. Next, I'll secure the electronics from the Switch 2 dock inside the outer case, and then slide the whole case on. I also use the H2D's laser cutting function to cut 2 black walnut decorative panels. I'll install an LED strip here, and slide it in. On top, I'll add the button and a decorative piece, and snap on the Switch 2 dock. It's on! Finally, let's add the metal nameplate, Nintendo Peaksbox 5. Success! A 3-in-1 console. I think it looks better than the PS5, you know? I didn't expect the finished product to turn out so beautiful. Every side has triangular elements, you can even feel them right here. This side houses the PS5, this side is the Xbox, and the last side is for the Switch 2. Just slide the Switch 2 in, press the red button, and it pops right out. Now all three consoles share one HDMI cable and one power source. Plug it in and the front light turns on. Right now the light is blue and the screen is showing the PS5. And now for this console's most magical and most important button, this triangle on top. Press it once. The light turns green and the screen switches to the Xbox. Press it again. The light turns red and the screen switches to the Switch too. Isn't that amazing? So convenient. I think it's just incredibly convenient. So now let's play some games and see if it can handle everything normally. Right now I'm playing a Switch 2 exclusive Donkey Kong Bonanza. It runs perfectly. Of course it does. It doesn't even need to cool down. It switched in under 5 seconds. That is so awesome. Playing games on the PS5 is also completely normal. So normal, it's almost unbelievable. But now, what if you suddenly want to play Xbox? Just press it again. The light turns green. And hey, we're on the Xbox. The Xbox runs normally too. After playing for a bit, whoa, the air vent on top is actually pretty hot. 3 platforms, all running normally on a single console. For a second, I was a little dazed. I can't believe this is actually real. It's like a feeling of world peace and harmony. The combination of old school methods and modern tech is just so beautiful. I'm pretty happy with the final result of this 3-in-1 Nintendo PX Box 5. At first, I just wanted to make a funny video. I didn't expect it to be so practical. And it looks really good too. I don't think it looks any worse than the original PS5, you know? It keeps the full functionality of all 3 consoles while also shrinking the size and making the cable management much cleaner. I hope it can keep on working for a long time. A warning to those who keep making exclusive games. Actually, I've been wanting to try metal casting for a while now. Even though home 3D printers are already magical enough, at the end of the day, they can only produce plastic. But now that I've learned a lost PLA casting, we can take all those weird and wonderful things we printed before with the Bamboo Lab printer and turn them into metal too. Now that's pretty interesting. So, if this project taught me anything, it's this. Don't assume your plan is going to be simple. You think it's as simple as connecting a few wires and 3D printing a case?